Even integrating something as easy as a polynomial can be rather surprising. Let's integrate from x equals 0 to 1, just the polynomial x plus 10 times x minus 1 to the 10th power dx. So there's some integration problems, just an integration problem for a polynomial. Your first inclination might be, oh, I know what to do, just have no fear. I'll just expand everything in sight. So we've got x plus 10 times x minus 1 to the 10th, which you could expand by, the binomial theorem if you want. What do you get? X to the 11th minus 55, x to the 9th plus 330, x to the 8th minus 990, x to the 7th plus 1,848 times x to the 6th. This is ridiculous. Yeah, so you could do that. You could just expand everything out. But there's a better way, right? We can make use of u substitution. Yeah, we're not going to do that, right? Let's do something else. So instead, let's set u equal x minus 1. And I could solve this for x. That means that x is u plus 1. And if I just add 1 to both sides. And I could make this substitution in this problem. So this integral from x goes from 0 to 1 is, well, what's x plus 10? If x is u plus 1, I could write u plus 1 plus 10. And what's x minus 1? That's just u to the 10th power. And what's dx? Well, if u is x, du is dx. So it's the same as trying to do this integration problem. In some textbooks, this technique of starting with a u substitution but then solving for x, this is sometimes called back substitution. Well, regardless of the name, let's proceed. So this is the integral, x goes from 0 to 1 of u plus 11 times u to the 10th du. I could expand this, and that's the same as the integral x goes from 0 to 1 of u to the 11th plus 11 u to the 10th du. But now this is just asking me to anti-differentiate a polynomial, which I can definitely do. Right? This is u to the 12th over 12 plus, what's an antiderivative of 11 u to the 10th? It's just u to the 11th. But now I've got a little bit of an issue, right? I've got x going from 0 to 1. So here it's u going from what to what? Yeah, so how do we deal with those endpoints? Well, when x is 0, u is minus 1. So I'll put a minus 1 there. And when x is 1, u is 0. So I'll put a 0 there. And now this is just as easy as plugging in 0, plugging in minus 1, and taking the difference. So what do I get when I plug in 0? I just get 0. And what do I get when I plug in minus 1? Well, I get minus 1 to the 12th over 12 plus minus 1 to the 11th. All right. Minus 1 to the 12th is just 1. So this is 1/12. And minus 1 to the 11th, well, that's negative 1. So I've got 0 minus, what's this? A 12th minus 1, that's negative 11/12. But it's 0 minus negative 11/12. So the integral is 11/12. So the calculation turned out to be pretty nice. 11/12 isn't a particularly difficult fraction to come up with. The crazy thing to think about is that we could have approached this just by expanding everything in sight. Yeah, I really could have expanded this thing out and then just started anti-differentiating, and finding that this really was, I don't know, x to the 12th over 12 minus 11 halves x to the 10th plus 110 thirds x to the 9th, right? And it would keep on going, and I just evaluate that x at 1, x at 0, and take the difference. I really could have done this by expanding. And somehow that would have ended up giving me the same answer, right, of 11/12. Except that had I gone down that path, I would have been certain to have walked right into an arithmetic error. The world of mathematical solutions is not divided into correct solutions and incorrect solutions. It's really more subtle than that. Mathematical solutions come in a ton of varieties, right? There's easy solutions and hard solutions. There's solutions that are defending you against arithmetic errors, and then there's solutions that are just walking you right into an arithmetic mess. The fun of U substitution isn't just being able to do integrals. It's being able to do integrals in an efficient way that protects you from those arithmetic errors.